For years I wanted to prove to myself that a geodesic and warped space-time could appear as the same type of acceleration that's demonstrated by an object falling to the ground. But if I don't have some kind of visual, I usually have a hard time understanding something. In most graduate-level textbooks addressing this subject, you're lucky to see even a single picture in the text. Fortunately, a wonderful, more accessible text by Sam Lilly called Discovering Relativity for Yourself inspired me to push myself towards visualized understanding in a difficult-to-visualize subject. I hope I have made worthwhile visual findings to the viewer, and I hope I can demonstrate them in a way that achieves the three main points of public speaking, which are the following. First, you must be heard. Second, you must be understood. And third, you must be pleasing. The classical tests of relativity, like bending rays of light measured in an eclipse and the precession of Mercury's perihelion, are a little difficult to deal with, and I figured something simple like an object falling from space straight to the Earth with no transverse motion and no air resistance would be a nice, easy setup for comparing a Schwarzschild geodesic with an inverse square law, and would be enough to convince me that bent spacetime could at least mimic the inverse square law, even if it's not sufficient to prove spacetime is curved by a large mass. To do this, I had to visualize gravity as an inverse square law first. I had always visualized a height versus time graph of a falling object as a parabola following the equation y equals -1/2 times 9.8 x squared plus an initial height, where x is time and y is height. But this is constant acceleration, and the acceleration from the inverse square law is not constant. An acceleration represented by an inverse square law would be d dx of dy dx equals k over y squared, where y is the height, x is the time, and k is a constant. Using an antiderivative, we can get dy over dx equals kx over y squared, plus a constant m. We can do it again to get y equals kx squared over y squared, plus xm plus another constant b. Now if I get rid of the constants m and b by letting them be 0, I get y equals kx squared over y squared. If we let k be 2gm, where g is the gravitational constant and m is the mass of the planet, we get y equals 2gm x squared over y squared. That is an inverse square law equation putting position against time, more or less. About as close as we can get to that. Interestingly enough, you can also derive this from the equation for escape velocity, where dy over dx equals the square root of 2gm over y. Then after taking the antiderivative in terms of x and then squaring, we get y squared equals x squared times 2gm over y, and we can flip the positions of the y and the y squared to get the same inverse square equation. Just letting something fall bears a strong relationship to escape velocity. I guess because you have to go at least that velocity at each point to keep from falling. Anyway, if we go to a graphing calculator, like the rather nice Desmos in this case, and plug in the equation y equals 2gm x squared over y squared, using the actual numbers for g and m of Earth in SI units, which I will use all through this video since they make things a lot more consistent and easy, gm is 3.985 times 10 to the 14th. We get a graph like this. Approximately these ranges were used. The x range from -3,000 to 6,000, and the y range from 0 to 1.4 times 10 to the 7. Because the distance y is measured from the center of the Earth instead of the Earth's surface, and the Earth's radius is pretty big, 6.371 million meters. Notice this graph assumes that the height of the object starts at a negative time and ends at t equals 0. We could change that, but it makes the graph more complex than we need for this demonstration. Now, how can we draw a geodesic on a Schwarzschild metric and compare it to our graph here visually? Do we need a brain like Hans Delbrück to do so? Here's how we proceed. First, we take a look at the metric, which we'll take as a given. It's ds squared equals 1 minus rs over r times c squared times dt squared minus dr squared over 1 minus rs over r. Messy and ugly, and this is only the part of the metric that's relevant to an object falling straight down to a planet's center with no transverse motion. We won't use any more of the metric than that. Fortunately, my aim here is not to derive the metric, but to simply show what a geodesic on this metric would look like. I need to know how to create a geodesic on this metric. Going back to ideas from Sam Lilly's book, it gives us a kind of formula for what a geodesic on this metric is, and I'll attempt to justify that idea somewhat. If you draw a graph with an r-axis and a t-axis, you can think of dr and dt as infinitesimal distances on this graph. On a graph where r and t would be flat space-time, dr and dt would be equal everywhere. But warped space has a varying dr and dt at different points. I've mentioned this in my past two videos because it's probably the biggest idea in differential geometry, which general relativity bases a lot of itself on. We can think of ds as the hypotenuse of a triangle completing the distance moved dt in the t direction, and then moved dr in the r direction. This isn't entirely accurate with the Schwarzschild metric because I think ds is actually smaller than either dt or dx here, but it'll at least give us a rough idea of what's going on. If we take this picture here and imagine that ds is always proportional to dt, no matter how long or short dt is, we'll get a geodesic, a line that doesn't bend to the left or right as you move across it. So we just need ds to be equal to some constant times the stuff that's in front of dt times dt and plug that into our metric to get a geodesic on that metric. Once we plug that in, we'll do some algebra to the equation to try to get to some graphable form that Desmos can handle. We'll do that here, trying to be very careful with all the easy to mess up algebra. We'll set ds equal to a constant b times 1 minus rs over r dt. Then we'll plug it into the metric. We get this equation. Then we divide by 1 minus rs over r to get this. Move the dt's to one side and the dr to the other to get this. Pull out the dt squared with the distributive property. Move the dt squared to the other side, and move the 1 minus rs over r squared to the right hand side. Last we put in terms of dr over dt. Now we have something pretty suitable to graph on Desmos or some other suitable graphing calculator that handles derivatives. Desmos can handle something in terms of dy dx, and we have a dr dt here. So we replace the radius from the planet's center, r, with y, replace the time t with x, and replace the rs with the Schwarzschild radius of Earth, 0.0089, and let the constant b be equal to the speed of light, roughly 299 million meters per second. And then this equation pops out. Sort of like how the actor's head almost pops out of the neck of the costume in Horror of Party Beach. Not enough that the costume was silly on its own. The actor couldn't even put it on right, and the director never bothered to correct him. I can graph this equation against the inverse square equation earlier, and I really see no difference. In fact, on this picture of both of the two, the only reason I see a difference at all is because I multiplied the inverse square equation, which is in orange, by a 1.1 term, just so I could see both of the graphs. Without this term, both of the graphs together would look just like one graph, and my visual would not appear as convincing. The Schwarzschild radius, which is not multiplied by any modifying term, appears in blue here. Now if I disregard that 1.1 term, I actually can notice a difference between the two graphs, but only if I zoom in very, very, very close, as we see an anomaly formed at the Schwarzschild radius in terms of the geodesic graph here. Well, hopefully this video had something enlightening about it for the viewer. I thought the ideas in it definitely helped me to understand how a geodesic on the Schwarzschild metric really could mimic an inverse square law of gravity. Now, if you'll pardon me, I'm off now to assist the lady in the radiator and hopefully protect her from that upcoming Sharknado headed her way.